Welcome to this lecture on graphs. Today we're going to talk about single source shortest paths and finding their solutions. Shortest path problems in graphs are very common. They are very practical and we want to solve them in lots of different contexts. There are many real world problems where shortest path problems are the natural type of solution that we want. So if you have to get from point A to point B, either on roads or on trails or in some other fashion. You want to get between two locations, the shortest route that's expressible as a shortest path in the graph that represents the places where you're able to go. Maybe you want to route information between computers on the internet or on a local network. The fastest way to route packets can be expressible using a shortest path representation solution to a graph, which represents the computer network. And if we represent our flight network in from city to city using a graph, and we want to say find the cheapest set of flights from city A to city B, we can represent that as a shortest path problem. So shortest here could mean distance, it could mean cost of some kind, it could mean time. The definition depends on our context. And so here, down here, we have perhaps a network, a graph that represents a network of roads between different cities, say, and if I wanted to go from city A to city C, right, there are at least two different routes I could take. I could go from A to B to C, and that would cost me a total of 1 plus 8, which is 9. But if I took a different route, if I went from A to D to E to C, that would cost me 2 plus 2 plus 2, or 6. So 9 versus 6, the shorter route is 6. And we want algorithms that can identify these cheaper paths, these shorter paths. Now, again, different contexts call for different algorithms. And different contexts, such as if we have an unweighted graph, then if we're talking about single source shortest path problems, which we are today, then we want to use breadth first search. Um, if the graph is unweighted and we want to do all pairs shortest paths, that means we want to find not just the distance from one source, but from all sources to all destinations. Then you can see in all circumstances, we want to use the Floyd-Warshall algorithm, which we'll talk about in a later lecture. If the graph is weighted, but the weights themselves are non-negative, they could be 0, but they can't be negative, then for single source shortest paths, we want to use the Dijkstra algorithm, which we'll talk about in this lecture. And if the graph is weighted and there could be negative edges, negative cost edges, negative weight edges, then we need to use what's called the Bellman-Ford algorithm, which we'll talk about in the next lecture. All of these algorithms, or at least many of these algorithms, the runtimes depend on the representation, the matrix versus the list. And we'll do analysis of these algorithms with respect to both of those representations. And all four of these algorithms work just fine on either directed or undirected graphs. We won't talk about the difference there, just assume that they work fine in both contexts, directed or undirected. In its general form, a single source shortest path problem has two inputs, a graph G, which is a set of vertices and edges, and one of those vertices specified, which we'll call S, the source S. And the outputs are usually one or two things. At the very least, we usually get the distance from S to every vertex in the graph. So you might be asking yourself at this point, why wouldn't you just ask the distance between the source S and your destination, which we might call T? Why do we ask for S to everything in the graph? Well, it turns out that in many contexts, including especially in weighted graphs, you often have to, in the worst case, answer the question of from the source to everything in the graph. You might be able to get away with just the destination that you're concerned about. But in general, most of these algorithms will solve the shortest path to everything in the graph. You can optimize that if you wish. The second thing that the single source shortest path algorithms output are the shortest paths themselves. So knowing the distance is not the same thing as knowing the shortest path. It's like knowing that Waco and Dallas are 90 miles apart doesn't help me to know how to get from Waco to Dallas or Dallas to Waco. it only tells me what the distance is. So actually figuring out what are the shortest paths could be a secondary output of these algorithms, but it's not a necessary thing. And sometimes we run these algorithms without figuring out what these actual paths are. Now, these shortest paths are in single source context from S to every vertex. And usually, we'll see this later, this information is reported as a tree structure. You can think of it as a tree structure using what are known as previous or back links. And these represent the shortest path to every vertex, what its predecessor was coming from the source. We'll see more in a minute. Now, let's tackle the first problem. The first context is if we wanted to find the shortest path between the source and every vertex in an unweighted graph. Okay. In this context, shortest path means least number of edges because there are no weights in our graph. Or if there are weights, we're just ignoring them. Another way of thinking about this is that every edge has the same cost, and that cost is, say, 1. But at any rate, we're just counting the number of edges. And the nice thing here is that we already know of an algorithm which solves this problem exactly, and it is breadth first search. Breadth first search, BFS, solves this problem. And the reason it solves this problem is due to the queue ordering, which we'll talk about in a minute. But the point is, if the source, let's take a look at this graph down here. If the source is this vertex A, the first thing that we do is we visit everything that's 0 steps away or 0 edges away from the source itself, which is A itself. Okay, so if we think about what have we explored, everything to the left of this expanding frontier that I've drawn here. Then we take that thing and we expand it and we look at everything that's 1 edge away or 1 step away. And that would be, in this case, B and D. And they get placed on our frontier, our queue. And then after we explore those, we visit everything that's 2 away, 2 hops or 2 edges away from the source, and so on. Okay? So this is the way that breadth first search works. This is the way we solve unweighted single source shortest path problems. Now, we should tackle the question, and this is an important concept, why does this work to find the shortest paths? In other words, in that search that we just did, why does the queue ordering allow us to find the shortest paths? Well, again, if this is our source, A, here's the general idea. If after some number of steps of this algorithm, when we say steps, we mean number of edges, okay? So 0 steps away from the source, 1 step away from the source, 2 steps away from the source, 3 steps away from the source. So we know that when we search this graph, we're going to find that this is 0, these 2 are 1, these 2 are 2, and this one is 3, okay? Here's the key idea. If we have not yet discovered or visited a node, which we'll call V, in fewer than k steps, so if we're at k equals 2, okay, and we haven't discovered vertex C yet. If we haven't discovered it in 2 steps, in fewer than 2 steps, so if we haven't discovered it in 0 steps or 1 step, that's what this first line says, and then we discover it in k equals 2 steps, then because we're visiting things in queue order, then k must be the shortest path, the distance of the shortest path, the length of the shortest path from S to that vertex V. Because if we could have found it in fewer than k edges, steps, then we would have, but we didn't. So the time at which we find it, the number of edges away from the source that we find it, that is the distance between the source and that vertex. Okay. So let's talk then about how to keep track of the shortest paths. And by the way, I want you to keep this intuition of why does breadth first search solve unweighted single source shortest path, because we'll sort of revisit this idea of looking at everything closest to the source and then everything a little bit further away and a little bit further away. We'll revisit this idea again in this same lecture. Now let's talk about how would we report the shortest paths themselves. If we wanted to tell someone how to get from point A to point B, we need to report these shortest paths. The way we do this is via something that we could call backlinks or previous links. And this is true throughout all shortest path algorithms, not just breadth first search. So this is a general idea. These links point from the node back towards the source. Okay, so they point back towards the place where we originated our search. And because of this, every node has at most one backlink. And because every node has at most one backlink, these things form a tree structure, which you can see down here. If I were to perform breadth first search on this graph with A as the source, then A would have its own predecessor, okay? It would point to itself as its own predecessor, its own previous or backlink. Then the first thing that A does is discover B and D. And when we discover B and D, we say which node led us to B and D. Well, A did. So B would point to A and D would point to A. Similarly, C would point to B and E would point to D and F would point to C. Now, the important thing to notice here is that there's another edge here that's not a backlink. It's an edge in the graph, but it's not a backlink because if we had discovered C through E, which we could, but not the shortest way, if we had discovered it that way, then we would have found a longer, shortest path, right? But the first way that we discovered C was through B. And so C has only one predecessor, and that is B. There could be ties because there could be multiple shortest paths in a graph, but we can break those ties arbitrarily. Now, what does this tree structure of backlinks give us? Well, it gives us an easy way to find these shortest paths by walking backwards through the graph, from the destination backwards towards the source. So if I wanted to know what is the shortest path from A to F, I would go to the destination, which is F, and walk backwards from F to C, C to B, B to A. And then A's self-link or self-loop tells me that it is the source, so I can stop looking there. And as I mentioned, all other shortest path algorithms use exactly the same idea. So we won't really revisit this again, but you can use this idea throughout all of the shortest path algorithms that we're talking about. Breadth first search works well and is the appropriate algorithm for unweighted graphs. But if the graph that we have is weighted, it does not work anymore because breadth first search considers all edges to have equal cost, and that's not true in a weighted graph. It could miss, and it will miss, lower cost paths that use more edges. So this was the example that I showed up at the top of the lecture. The distance from A to C is 9 if I go on the top and 6 if I go on the bottom. And of course there's a difference. This one at the top uses 2 edges, on the bottom uses 3 edges. Breadth first search would select the one with fewer edges but greater cost. And so we need an algorithm which would select something that has more edges but lower cost. And the solution to this is to simply replace our queue with a priority queue. And I think a lot of people get intimidated when they hear of this next algorithm, Dijkstra's algorithm. Dijkstra's algorithm, named after its inventor, Edgar Dijkstra, a Dutch computer scientist. But I want you to not get overwhelmed here because I want you to think about this algorithm as breadth first search, but with a priority queue. So we're just mostly what we're doing is just replacing the plain queue, which is first in, first out, with a priority queue, which is the highest priority thing out. And when we have a priority queue, we have to specify its order. And that priority queue could be something like a min heap or something like that. And so the thing that we're going to order a priority queue by, the priority that we're going to give to the vertices that we're going to store in this priority queue, is the total path cost from the source. So when we store things in the priority queue, we're going to store actually pairs. When we talked about breadth first search, we just stored in that queue just the vertex itself, or at least we could get by with that. Um, in this priority queue, we don't want to order things by when we put them in. We don't want to order them by the vertex themselves. We want to order them by this thing, the total path cost from the source. So that has to be a part of what we're using to order the priority queue. So it has to be part of the element that we're storing in the priority queue. So that is the first thing that we put into the priority queue element. But we need to store which vertex are we talking about. So that's the second thing. So the cost comes first. That's the total path cost from the source. And then the vertex comes second. And the cost comes first so that if we're making comparisons by first things first, the cost gets compared first. Let me peek ahead here. So before we talk about how Dijkstra's algorithm works in particular, I want to introduce an idea that we're going to use more than once, and that is the idea of relaxation, which is a nice concept to talk about. The technical definition for relaxation is given here, um, and we're going to use it in multiple shortest path algorithms. The basic idea is this. It asks the question, can I get from vertex A to vertex C more cheaply with less cost by using some intermediate vertex B? Okay. And if so, update that distance from A to C and the predecessor of getting from A to C to go through to indicate that it should go through B. Okay, so before I show you the code down here, it's basically asking this question. If I have vertex A and I have some known way, or maybe some way that I don't know about, could be in infinite cost. If I have some way of getting to C, and I've drawn this as a squiggly line because it might go through many intermediate vertices, and it has some cost, let's suppose it has a cost of 10, okay? And then maybe there's some intermediate vertex B, which has some way of getting to C, and there's also some way of getting from A to B. And maybe this has a cost of 3, and this has a cost of 2, right? If what I previously knew was that there's a cost of getting from A to C of 10, but I just investigated and I found, well, I could get from A to B in 3 and B to C in 2, clearly that's cheaper. So we're going to relax the cost of getting from A to C from 10 down to 3 plus 2 or 5. In addition, when I do this, I'm going to point from C to B as my backlink, okay? And that's what this code does down here. Relax from A to C with possible intermediate vertex B. And here's the code. If the distance, the current estimate of the distance from A to B, plus the current estimate of the distance from B to C, is cheaper than the current estimate of the distance from A to C, those are the three numbers that we drew down here, or up here, then we simply replace the distance from A to C with this cheaper sum of distances going through B. And also, we let the backlink for going from A to C point from C backwards to B. Okay, and that's only if we need to track these shortest paths. So again, this is called relaxation. The notion here is that your sort of graphs are very tense if they have great distances to travel, and if you can reduce those distances, it's kind of the sense is that you're relaxing these distances. So we'll use this in Dijkstra's algorithm and other algorithms. Now let's look at the meat of Dijkstra's algorithm. Again, Dijkstra's algorithm input is a graph and a source, okay? We initialize here in these first three lines, and the initialization is just initially the distance from the source to every other vertex is infinity, except for the distance from the source to itself is 0. And we're going to place onto the priority queue, which we'll call Q, we're going to place the pair 0s. And again, 0 represents the cost of getting from the source to that vertex, and s is the vertex. Okay, and clearly starting at s has a cost of 0. So we're going to proceed as follows. While the queue is not empty, we'll remove from the priority queue the lowest cost vertex with cost, which is x, with cost c. Okay, so that means we have some vertex x, and we know that from the source there's some path to get to x, which has cost c, and we just pulled x and its cost out of the priority queue. Then for each of the edges that leaves from x that goes to y with cost d, so this is a direct edge from x to y, um, we ask the following. Is it possible that c, and I'll write the cost is d here, c, which is the cost of getting from source to x, plus d, which is the cost of getting along that edge from x to directly to y, if c plus d is less than my current estimate of the cost of getting from s to y, okay, so that's this quantity right here, then, and this is relaxation, let the distance of s to y be c plus d, relaxation. And in addition, we're going to have to place y onto the priority queue with the cost of c plus d. And I have a note here that says, or replace it. What does that mean, or replace it? Well, that means that maybe y was already on the priority queue with a higher cost. And in that case, I could just reach into the priority queue if I had the ability and lower its priority from what it was, which was dist from s to y, down to c plus d. I can do it either of these ways. I can duplicate y on the priority queue, or I can just keep a single y on the priority queue with the corrected cost. And either way works because the lower cost, if I have duplicates, then the lower cost version of that vertex will come out of the priority queue first. I realize that I'm just going to backtrack for just 1 second onto this relaxation slide. I want to point out one important thing, that these 3 steps can be done in constant time. Okay, so relaxation, anytime we want to relax, we're doing that in constant time because we have simply an if statement, some additions, some comparisons, and some assignments. And notice here, we have the relaxation step right here, okay? In addition to updating the distance, we might also update the backlinks in here, which I haven't written down, but we would update the backlinks if we wanted to keep track of these shortest paths. Okay, so let's do an example of Dijkstra's algorithm. Here's the main loop that we just looked at from Dijkstra's algorithm. Assuming that the source is A, we're going to have our priority queue, Q, and we're going to initially place into that priority queue the pair of 0, comma A, right? Because that's the cost of getting to A from itself. All the rest of these vertices have initial cost of infinity, which I won't draw on there. Okay, so while Q is not empty, well, Q has that on it, so I'm going to remove CX from Q. So C and X are 0 and A. So I remove those from the Q, and then I'm going to look at each of the edges going out from A, which go to B and D. So in this case, C is 0, and if I'm looking at B, then this cost D is 1, okay? And the question is 0 plus 1 less than my current estimate of the distance to B, which is infinity at this moment? Well, yes, it is. So I'm going to update the cost of B, of going to B, and I'm going to put onto the priority queue C plus D and this vertex B. So I'm going to put onto the priority queue 1, comma B. And I'm going to do the same thing for D. So D will get 2, comma D on the priority queue. It has a cost of 2, and we continue. Okay, so we loop back around. We say remove the next thing from Q. Well, what should we remove? We have 2 items on the queue, but we should remove the one with the least cost, and that's 1B, because it has the cost of 1. So we'll remove 1B. At this point, we have found the shortest path to A and to B, but not necessarily to D. I mean, it will turn out to be the case. But it's only, I want to point out that this is the point where you know when it comes out of the priority queue that you've actually found the shortest path. Removing B from the priority queue, I look at all the outgoing edges, which go to A and C, and clearly going back to A is not going to improve the cost of getting from A to itself. In other words, going from A to B to back to A doesn't help things. In other words, 1 plus 1 is not less than 0. So that's not going to change anything for A. But going from B to C, I have a cost of 1 to get to B and 8 to go from B to C, which is a cost of total 9. And the previous cost estimate for C had been infinity, so I'll mark 9 and put 9 comma C on the priority queue. Continuing, I'll pull something else out of the priority queue to D. 2D leads me to A and E. Clearly A is not going to improve, but E will, with a cost of 2 plus 2 is less than infinity, so 4. And we'll put 4 comma E on the priority queue. And I want to point out now, E was added to the priority queue after C, but it gets higher priority because 4 is less than 9. So the next thing that we're going to pull out of the priority queue is 4E, not 9C. And this is where Dijkstra's algorithm shows the difference with breadth first search. So 4E gets removed from the priority queue. We look at the neighbors D and C. Both have been visited so far, but we can actually improve the distance to C, right? When we do this relaxation step on the vertex C, we currently have 9, but we could reduce that down to 4 plus 2 is 6, okay? So we're going to change this 9 to 6, and furthermore, we're going to put 6 comma C on the priority queue or replace it. And when I say put 6 comma C, I mean literally put 6 comma C on the priority queue. And as I said before, if I duplicate C in this way, it's okay, because 6 comma C will come out before 9 comma C, and the first version of the vertex that comes out is the shortest path. However, in this class, I like to encourage you to replace the value here, because then we don't have duplicate vertices on the array queue. I'm sorry, on the heap, the priority queue, and it saves some memory. Okay. So the next thing that we'll pull out of the priority queue is the only thing on the priority queue, which is 6C, and that leads us to, well, multiple things, but the most important one is F, which we can reach in a cost of 9. So we put 9 comma F on our priority queue. Then the next thing we do is remove it. We can't get anywhere else from there, and we're done. Okay. So the shortest paths from the source to each of these vertices is as we see here. And the backlinks for each of these would be the vertices that led us, whoops, and that's not correct, that led us to the source, from the source to that vertex. And you'll notice that when we first discovered C, we would have had its backlink be pointing to B, because that's where we first discovered it with a cost of 9. But then once we updated its cost to 6, we changed its backlink to be E. Okay. So let's talk about correctness. Why does Dijkstra's find the shortest paths in a weighted graph? The reasoning is similar to breadth first search. Dijkstra's algorithm visits everything that is 0 distance from the source, which is the source itself. And then it visits everything that is just a little bit further, and then just a little bit further. And this priority queue ordering progressively increases the distance that we're willing to consider for which vertices are within that distance bound. And we only consider things that are as close as possible to the source at each step. So again, the distance from S to V is the distance of the shortest path from S to V, or our current estimate of that shortest distance. And we're visiting these vertices in increasing distance order due to the priority queue. And the argument is pretty much the same as with breadth first search. If we could have found a path in lower cost, we would have done so. So as our priority queue tells us, visit things that are 0 distance away from the source, and then distance, 1.5, and then distance 7, and then distance 9, and so on. If we're at distance 9, and we haven't discovered the shortest path to some vertex yet, and then we get to distance, say, 12, and we do discover the shortest path to that vertex, that is the shortest path. And that, I want to emphasize, that is this point right here. This is where we find the shortest path, is when we remove that vertex from the priority queue. Not when we first discover it, but when we actually remove it from the priority queue. Okay. So if we could have found a shorter path in lower cost, we would have done so. In other words, every time a vertex comes out of the priority queue, it's the closest vertex at that distance. There are no other vertices that we haven't processed that are closer. So it must be the path that we found to that vertex must be the shortest path. Another way of thinking about this is that leaving and returning, once we've discovered a vertex and its shortest path, if we left that vertex and then returned, so in other words, we have some vertex and we know that the source to that vertex is some distance, we couldn't then, leave this vertex and then come back via some other intermediate route without increasing the distance to this vertex. Okay. That's under the assumption that all of the edges are non-negative, and we'll talk more about this in the next lecture. In other words, this path, if all the edges are non-negative weights, then this could only increase the cost, or at least at most keep it the same. So let's do the analysis of Dijkstra's algorithm, and we're going to do the analysis twice. Once with a list representation with a priority queue, as you see here, and once with a matrix representation without a priority queue, which we'll see later. Okay. This while loop is going to iterate v times, as I say here. Now, why is it going to iterate v times, or at most v times? Because every vertex gets placed onto the priority queue and then removed from the priority queue. So that can only happen v times, okay, if we're using replacement when we discover shorter paths to vertices that we've already discovered. So the priority, and that's this is the argument that I just made. The priority queue holds at most v items when we're using replacement. Now, if we didn't use replacement, the priority queue could hold up to on the order of v squared items. In other words, there could be v copies of each vertex, and there are v vertices, so we could have on the order of v squared things in this priority queue. It turns out that that's not a big deal, okay? Either way, whether we have v items or v squared items, the cost of removing from the priority queue is log v for most priority queues, like a binary min heap. And you might say, but how could it be the same for v or v squared? Well, because we know that log of v squared is equal to 2 log v, and 2 is just a constant here. So big O of log v squared is equal to big O of log v, okay? So we have v iterations here. This cost is log v, and then we have to iterate over all the edges, okay? The total iteration over all the edges is E, and that's over all outer loop iterations, okay? So the point here is that we might have V things iterating here, but if we go over all the edges in the graph, there are only E total edges in the entire graph. So this is not V times E. This is E over the course of the entire algorithm. And that's just a more convenient way to analyze this than thinking about, well, for this vertex, it might do this many edges, and for that vertex, it might do this many edges. No, let's just count over the entire algorithm. How many times does line 3 execute? It's going to execute E times. And how do we know that? Because we can enumerate all of the edges in E time if we're using a list representation. So this type of analysis is a little bit different than what you might be used to. Then finally, um, this relaxation step, these two steps right here, and adding the backlink if we need to, are constant time, so we can step over those. But if we have to put something into the priority queue or replace it, this costs us log v time, okay? So the total cost for this algorithm is we have order v iterations here. This is log v here. We have e over all iterations here, and then we have log v to insert or replace on the priority queue. So what is the total runtime? The total runtime is v times log v plus e times log v. And again, we don't multiply this v times this e because this e counts over all edges in the entire graph, which we're only going to visit each edge once. And e times log v, because we might have to do an update where we insert into the priority queue each time. So E log V for, again, a list representation using a priority queue. Now, if we use a matrix representation, it turns out to be faster to not use a priority queue. So everything that we've talked about with priority queues, you can do that with a list, and that's what you would want to do. But if it turns out if you're using a matrix, you're actually better off not using a priority queue. And then you might say, but how do you find the next vertex to visit in Dijkstra's algorithm? Well, we'll talk about that in this matrix-based Dijkstra's algorithm. The first thing you'll notice is that we're doing this for v iterations. Okay, we're not saying while the priority queue is not empty because there is no priority queue. So we'll just do this v iterations. And we'll say we're going to find the being visited vertex. Now, we didn't use this term in this lecture, but you recall that being visited means I've discovered the vertex, I've placed it on my priority queue, but I haven't pulled it out of the priority queue. Okay, so being visited means essentially it's been discovered, but it hasn't been used, extracted at this line of the code as we found the shortest path to this vertex. So among all the vertices that have been discovered but not yet plucked out to be processed, we find the one with the lowest cost, and that we'll call that x. Okay, and I don't say it here, but we'll say with cost c, right? And then for each edge that goes out from x with edge cost d to vertex y, if c plus d is less than the distance to get to y, then this is relaxation. We know how to do this, and we do these things, and we update the backlink if necessary. But notice one thing that's missing down here is there's no insertion into the priority queue because there is no priority queue. Okay, so this is the same algorithm. It's just we're using a matrix representation, and let's look at the analysis for this. The outer loop up here obviously uses v iterations. The cost at line 2 looks really expensive because we have to look at all the vertices, and we have to look at, of all these vertices, which ones are, currently have a non-infinite cost but haven't been processed, and which one of those has the least distance. And the cost of doing that is looking at all the vertices, so it's order v. And that's pretty expensive. Remember that we could do this in a priority queue with a priority queue in log v time. Okay, so already you can see this is already a v squared algorithm, right? Because we've got v here and v here, and we multiply those together. Now, at line 3, we have to check all the edges that leave from vertex x. We don't know how many edges there are from vertex x. And if you recall our previous conversation, you go to the row for vertex x, and then you have to look at all of the potential outgoing edges from x and say, are you an edge? Are you an edge? Are you an edge? And that costs v time. So that also is pretty expensive. Okay, but that's order v time per vertex. not over the entire algorithm like we did when in our analysis of the list-based Dijkstra's algorithm, where I said this line was order E. No, here we have order V just for the vertex X. Okay, so the total cost here is we have V vertices with a cost of V here, a cost of V here, and then all of this is constant time. So we can basically ignore that from our analysis. So we have V times V, whoops, plus V times V. So the total is V squared, okay? And again, like I say, you can do the analysis for yourself. If you added a priority queue to this to make step 2 faster, it would actually end up making things slower down here in the innermost parts of the algorithm because you'd have to insert uh, uh, into this priority queue, and you'd end up having V times V times log V, so it'd be V squared log V. So again, we have two representations and essentially two different Dijkstra's algorithms. If we're using Dijkstra's algorithm, let's look down here. If we're using Dijkstra's algorithm with a list, we get E log V. That's using a priority queue. If we're using Dijkstra's algorithm with a matrix, we're using V. It's going to take V squared time without a priority queue. Okay. Compare this with our breadth first search, which we've done the analysis of in previous lectures. E plus V for a list or V squared for a matrix. And if you compare those with the size, well, the size of a list-based graph is E plus V, and the size of a matrix-based graph is V squared. So you can see that both breadth first search and Dijkstra's algorithm using a matrix are as efficient as reading the graph itself, but they differ in their cost and their runtimes. Uh, for the list-based representation, breadth first search E plus V is as fast as reading the graph, but Dijkstra's algorithm E log V is a little bit slower than the cost of just reading the graph. So those are two classic and great algorithms, breadth first search and Dijkstra's algorithm for tackling single source shortest path problems in unweighted and non-negative weighted graphs. And next time we'll talk about how to deal with graphs that have negative costs on their edges.